Okay, so on Monday we talked about the Gibbs Sampler, and we said this is useful in the hierarchical model because in a hierarchical model, the conditional distributions are kind of naturally set up. Okay, which for a Gibbs Sampler, figuring out the conditional distributions, the univariate conditional distributions, where you condition it on everything else, that's often the hardest part. Okay, and so here we can we'll continue on in our baseball example, and in our hierarchical model, we say the parameters alpha and beta are coming from some kind of distribution, okay? And the alpha and beta are used to then determine the beta distribution, okay? So the beta distribution has two shape parameters, and those shape parameters are drawn from some unknown distribution. And once you have your beta distribution set up, then you draw theta values from the beta distribution. So again, the beta distribution is a distribution representing kind of probabilities or proportions, values between 0 and 1. So we're going to be drawing different values of theta. Okay, all of these are going to be some value between 0 and 1. And most likely the shape of our beta distribution will be concentrated around, 0.27-ish or something like that, okay? And again, the idea is, in our original baseball example, we had, for our prior distribution, the shape parameters 81 and 219, but rather than just using these as fixed values, we're going to treat those values, 81 and 219, as random variables, alpha and beta. We're going to say, I'm not ready to just say the number is 81 and the number is 219. We're going to say they themselves are random variables. So they determine our beta distribution. From our beta distribution, we draw each player's theta value. And then each player, goes to bat and either gets hits or misses. And that is the data that we have, okay? So this is week 9, here. Week 9, Wednesday. Okay, so we're continuing on in our hierarchical model. So I've got my and so our y is going to be some matrix. Maybe we've got 40 rows. Okay, one row per player. And then we've got, the outcomes of each bat. Outcomes of each at bat. All right, and then the unknown parameters. We have theta 1, theta 2. The theta values for each player, and then we also have alpha and beta. Okay. So, I might, just for simplicity, I'm going to just group these together, all right? And so our Bayesian hierarchical model basically has alpha and beta determine our theta, and the plate plate diagram, and this determines our y. Theta sub p. Okay. And our posterior distribution for the unknown values given our data will then be, all our theta values, the alpha, the beta, given our data y. And this is going to be the likelihood times the prior divided by the marginal, right? Okay. And I'm going to just ignore the we'll ignore the constant on the bottom. And we can factor this into, each y times each theta. Okay, so the hits and misses depend only on theta, right? And then the thetas only depend on alpha and beta. So this part, maybe I'll color this. So the likelihood of our data simplifies to this, and then the prior can be factored into this. Okay. Prior distribution factors into these two parts. And we might say that alpha and beta themselves are going to be is uninformative, right? So the distribution for alpha and beta are uninformative, okay? Prior distribution for alpha and beta is okay, and maybe we disagree on that, but that's okay. All right, so we've got this. So we've got probability of theta given alpha and beta given y is going to be proportional to the probability of y given theta, probability of or vector theta given alpha and beta, and then the distribution of alpha and beta is just going to be flat, so that's a constant, and so that disappears as well, right? And then, okay, and then for the Gibbs sampler, okay, we can draw theta sub j given alpha and beta and y sub I becomes a beta distribution with shape parameters alpha plus the number of successes, and beta plus the number of misses. Okay, and we'll do this for all kind of 40 theta values. And then the other part, we need to figure out what's the probability of alpha and beta given kind of our theta and our y. This is going to be the probability of alpha, beta, theta, and y divided by the probability of theta and y. And we can just say this is going to be proportional to kind of, what we factored out. Y given theta and theta given alpha and beta times probability of alpha and beta, but this is, a constant. And for this part, rather than trying to figure out the conditional, we can just do a metropolis step. Okay, so we can do Gibbs steps for theta 1 through theta 40, and then for alpha and beta, we can do kind of a metropolis step, right? And then we got to figure out alpha and beta, and it'll be kind of bivariate, but we can kind of mix the two together, and do a metropolis algorithm for these two, because finding the conditionals might not be so easy. Okay. All right. Does this kind of make sense, what we're trying to do? All right. All right, so let's, I guess we can code this. And first, let's generate our data. Generate our data according to the hierarchical model. Okay, so we will just say, we'll have shape 1. I'm going to just do shape 1 as 81. And shape 2 is 219. That's fine, okay? And then so my beta distribution will be then used, and so I'm going to have thetas will be R beta, and I'm going to get 40 values from using shape 1 and shape 2. Okay, and so I'm going to get 40 different values of theta here, okay? And then for each theta, I guess we can just do like, we'll do like 15 at-bats, okay? We'll have 15 at-bats for each player. Okay, and then so I'll just set up a Y matrix. Will be a matrix of, I guess I'll do NAs. Number of rows will be 40, and number of columns will be 15. And I'll say for I in 1 through 40, then kind of my theta will be from the thetas, we'll select the I, and then the hits will be R by gnome. I want 15 at-bats. Yeah, I want 15. Size is 1, and probability is theta. Okay, and then we're going to append this to this. All right, does that make sense? So this will generate our data y. So I got shape 1, shape 2. Here is thetas, okay. I've got 40 theta values. I can create a histogram of the thetas. All right, and so these are our different players' batting averages. And then we're going to set up a matrix, and for each row, basically I'm going to just say, all right, what is, what's my first theta value, 0.259, and I'm going to say, all right, I want 15 R binom, 15 values, and the probability is going to be equal to this, and so these are the results of the hits and misses for player 1, okay? And then we say, all right, what about player 2? And then we go do that, and this is what we get: a bunch of misses and a few hits, okay? And so we'll go ahead and we'll fill out our matrix like this, and let me just do. Let's just take a look at the kind of the first 5 rows, and we got hits and misses. All right, so this is our data. Okay, and so now we're going to pretend we don't know what 81 and 219 are, and we don't know these thetas. Okay, so using only the data, can we figure out the missing parameters? All right. Okay, so I guess I can remove shape 1. And we'll remove shape 2, and we'll remove thetas, okay? So all I have now really are just the y's. So let's see how we want to do this, okay? So we're going to just draw a bunch of these things. So in each iteration, so I'm going to just code up one iteration here. We're going to kind of get a sample of theta values, right? So I guess our sampling matrix, I guess we'll create a results matrix. This will be a matrix. Maybe I'll have 100,000 rows. Maybe this is too much. Okay. Number of rows will be 100,000, and then number of columns, we're going to have 42. Okay. And then what we're going to do is we're going to figure out our theta values. Maybe I'll call this, so I'll do for I in 1 through 40. You know, we just have to start off with some arbitrary values, right? So I guess we can just do kind of our initial values, initial random values. We'll draw thetas. We'll ask for 40 random uniform values, and then I'm just going to arbitrarily pick kind of alpha to be, I don't know, we'll say 20 and beta to be 20, okay? And then so in our first results row, I'm going to put in our thetas, our alpha, and our beta, okay? So we're going to just kind of put this into our first results row. Okay. And then, so our current thetas, I guess, so we need to draw a new theta value, right? So we're going to do the Gibbs Sampler, which is for each thing, we're going to go draw a new random beta using alpha plus k and beta plus n sub j minus k. Okay, so we're going to do shape 1 is going to equal, so I guess I have to build kind of an outer loop here. So this will be for j in 1 through 100,000, okay? We're going to draw kind of our current alpha value. So our alpha is going to be equal to results, comma, j, in the jth row, the first row, and we want the 41st value is going to be our alpha. Maybe I'll call this alpha current, alpha C, and alpha B, I'm sorry, beta C. Our current beta value will be results j comma 42. Okay, so I'm just pulling out the current alpha and the current beta value that currently we have. Okay, so in our first iteration, this will be 20 and 20. Okay, and we know those are bad values because we know that the true values, like we already have the answers that we used 81 and 219 to generate our values. So we know those are wrong. Okay, but right now we're just going to use our current alpha values, and so our what we're going to have, our first shape parameter will be alpha c plus, and we want the sum of our y matrix, the ith row in our y matrix. Okay, and then shape 2 will be our current beta value plus 15 minus the sum of y sub I. Right? So we're going to take the number of hits and the number of misses and fix our shape parameters that way. And then we will ask for a random beta using shape 1 and shape 2. Right? And this, we'll call this I guess I have to create a theta current or something, or theta sample, I don't know, something. Where I'm going to just repeat 0 40 times, and then we're going to store this for each of our players, right? So theta sample I is this, okay? So we do this for each of our 40 players. We update their theta sample value, okay? And then now we have to do a metropolis step to get a new alpha and new beta value, okay? So I'm going to have to do alpha propose and beta propose, and somehow we're gonna I'm just gonna do our norm centered at the current, ran out of battery here, centered at the current alpha value. And then centered at our current alpha value. I don't know. I guess I'll do standard deviation 1. I don't know. Is that okay? And then we'll propose a new beta value centered at our current beta value. Okay. And then do we accept or reject? All right, so now I should come up with a function to calculate the probability. All right, weird. Probability of this, right? So I'm gonna come up with a function to calculate probability of y given the thetas and the probability of the thetas given alpha and beta. And really, if we're just looking for alpha and beta, okay, well, so let me define a function. So this will be, I guess, our p function. P will be a function of kind of the proposed alpha and beta, right? Alpha propose and beta propose. And here we would need to figure out the probability, the total probability of theta given our alpha and betas, right? So we would need to do d beta of all of our current theta values. Okay, so actually we need to have our theta vector. So it's the theta vector given our proposed alpha and proposed beta. Okay, and so this is going to give me a like 40 beta distribution densities. Is there a log option here? Yeah. And because this, if I did the product of all of these things, it's going to be incredibly small. So I'm going to go ahead and use the log. So this will give me the log probability, the log, I guess the log probability of theta. It's going to be this. And then we also need, given our theta vectors, we need to figure out the probabilities of our y's. And if I think about this, then the probabilities, yeah, okay, so we'll get, I have to do d binom of, so I have a, will this work? Okay, let me just see. If I do d binom, let's say we had like 2 hits and 3 hits, size is equal to 15, and can I give a vector of probabilities? Like, .1 and 0.9? Is that right? Yeah, oh, nice, okay. So you can do element-wise operations for d binom. Okay, that's great. So I'm going to do d binom. We want to do basically the row sums of y. Size is 15, and the probabilities that correspond to will be our current theta vector. Am I going too quickly here? Is this okay? Does this make sense? So all I'm doing is I'm just trying to compute this. So I've got thetas given our alpha and beta. We have 40 of them. So I give it the entire vector of thetas given the alpha and the beta, and I'm turning them into logs. And then over here I want the y's given our thetas. We've got 40 different thetas, and we've got 40 different rows of y. So I'm saying I want the row sums of y, and then we've got a theta vector here, and we're going to get kind of the binomial probabilities. So I'm going to have the log of basically our y's, and this is going to be the sum of all of these things. And then what it's going to return will be the log probability of theta plus the log probability of y. I really hope this works. Let's just try this. Okay, so I've got y is this giant matrix, and I've got thetas. Okay, so let's just try probability of, let's try 20, 20, and thetas. Okay, it gives me a number, and then let's see if we get something better if I plug in 81, 219, or something else, 40 and 20 or something. Okay, yeah, we're getting all sorts of things. Right now, our thetas are just random uniforms, so of course it's pretty bad here. Probably the best will be. Okay, yeah. So there we go. All right, so we propose this, and then my p move is going to be the comparison of the proposed. So I've got alpha propose, beta propose, and our current theta vector, which is our current theta sample. Okay, we've just updated those. Okay, so everything's conditioned on everything. And then because we're dealing with log probabilities instead of division, I'm going to do subtraction. Okay, does that make sense? So we're going to do, and then I would use alpha current, beta current, and actually our the same theta sample, because we're really just testing the alpha propose and beta propose. Okay, and then we'll do R unif. U is going to be R unif 1, and we're going to take log u. If log of u is less than p move, which is already a log probability, then we accept, and otherwise we reject. All right, so accepting is going to mean my update is going to be the vector of theta sample along with alpha propose and beta propose. And if we reject, the update will be, we'll use beta current and alpha current. I'm just coding this on the fly, so I don't know if this is gonna 100% work or not. Okay. So this just says use our latest results for current values. This is a Gibbs sampling for each player's theta. And this is Metropolis propose new values. Oh, you know what? I need if alpha p is less than 0, we need to return 0. Okay. We just need to kind of have a check. If if we're proposing a value less than 0, we need to return 0. Okay. Just so we don't crash it. Okay. All right. So this is our Metropolis. This is the Metropolis p move, log of p move. Okay. And then we compare the log. Okay. And then lastly, we update our results. Results location j sub I, or j plus 1, is gets whatever is in update. All right, I really hope this works. Let's just try like let's only do 10. I don't know. We'll see. Let's only do 10,000. Okay, just before we crash our. All right, does this look okay? Is are there any questions on this the coding here? All right, does it kind of make sense what I was trying to do as I coded through it, talking through what I'm trying to do? All right, well let's just see if this this works. Okay, so we're gonna do shape 1, shape 2, our thetas. We've got oh, I guess I just generated a brand new I'm sorry, I got brand new data here. All right, so we're gonna just start off with arbitrary values of alpha and beta, which are probably bad. We have a function to calculate our probabilities P. We're gonna create an empty matrix for our results, and we're just gonna run this thing. Okay, we got an error, subscript out of bounds. All right, okay, so we're trying to go to j plus 1. What is our j? Our j is 10,000. Oh yeah, we reached the end of our thing. Okay. All right. Well, let's just take a look. All right. So the oh, I should have saved our thetas somewhere. I know I removed them, but I should have saved them somewhere. Okay, well, that's all right. Let's take a look at like maybe our column, 41st column. This is our alpha, and then let's just plot what this looks like. What is my, oh, sorry, not y, results. Okay. All right, my step size is probably too small. We started off at 20, but then it climbed up and it got to around 80-ish, okay? I probably need to tweak my step size. As far as the beta value, okay, we started off at 20, and by sampling, it climbed up to around 200, okay? So, I mean, this is promising, okay, that it is moving in the right direction, right? Because we know that our original alpha and beta that we used are 81 and 219, and our Gibbs Sampler is trying to figure out what those values are, okay? It says, you know, we don't know what the alpha and the beta are that were used to generate these things, and it's trying to figure those things out. Probably in my proposal, I probably need to take bigger steps than a standard deviation of 1. So I'm going to kind of just tweak this to say 3 each. I'm going to go ahead and instead of removing the thetas, I'm going to rename the, call these things theta originals. And then I'll get rid of the thetas. Okay. We'll go ahead and we'll try running this again. And I guess I should go up to 9,999. Okay, all right, let's we'll run our script. Nope, something. If log u is less than p move, there are 42 warnings. How far did we get? No, we crashed. Must have done something. I broke something here. Just leave this. Okay, we have this. Now I've broken. Okay, what is shape 1 and shape 2? That seems okay. We crashed after our 44th iteration. Did I do something? Oh, I'm proposing values of 3. Oh, I see. I know what's going on. Basically, I'm proposing something below 0, and so this is returning 0. Oh, but we can't return 0 because if I do log of 0, I get negative infinity. Okay, so I can't return 0. I've got to do like 1e to the minus, I don't know, minus 100 or something really bad. But not return 0 because that's going to cause a negative infinity. Log of negative infinity. Log of 0 gives me negative infinity, and that's going to cause my program to crash. Okay. All right. I know this is one of the hardest things in R is figuring out what the error message is and figuring out your problem based on the error message. So the reason how I figured this out was it says log of u is less than p move, and it says missing value or true false needed. Okay, which means I'm getting an NA here, okay? Which means there's something wrong in the comparison between log u and p move, and by seeing log u, that tipped me off that it's causing an issue here. Okay, let's see if we get any better luck here. We'll go ahead and clear everything out. We'll run it. Oh, wait, no. How do I run my script? Okay, we want to run everything. I'm still getting errors of p move. P move is missing here. All right, let me just see what's going on. So this is 22. All right, I'm sorry, something's going on here. That results 41. Yeah, it's giving me, it should say, it should reject this. All right, I have to figure out why. Maybe my step size is too big here. Okay, we're gonna run out of time. It worked kind of in the beginning with a step size of just 1. But somehow when I increase the step size, we're crashing. I think if I run this long enough, we'll get good results. But I have to figure out what's going on here. Okay. So yeah, this looks promising. This looks promising. I think there's just some issues with the step size. But okay. Well, this was kind of coding up a Gibbs Sampler / Metropolis algorithm blend for a hierarchical model. I'll go ahead and post the code. You can kind of read through it and see if it makes sense to you guys. So, all right, we'll end there. We'll see you guys on Friday and talk some more about this. Okay.
I was trying to run the code and it said